So let's move forward. Jeff, this is your review, a fresh look at storage performance with PCI Express SSDs. Now, you've been beating SSDs up lately. You did your endurance report, which was abusive, frankly somewhat disturbing, and a little bit sad. But now we're talking about SSDs in a slightly different format. This is, of course, the PCI Express, touted for its extreme sort of throughput capability through the PCI Express sort of channel on the motherboard. Is this a technology, Jeff, that's you think really going to start taking over, and why or why not?
Yes, but maybe not for the reasons that people might expect. You know, since SFDs have been around, they've used the serial ATA interface that has been with us forever at this point. And that's great for compatibility. You can plug them into any system. But especially you're noticing now with notebooks, they're too thin for sort of the standard 2.5-inch drives that have SATA interfaces. They've designed this M.2 interface that's largely built around PCI Express. So just because of how important mobile is and the fact that you know, the bill of materials for a small little gumstick style M.2 SSD is probably going to be a lot lower than for a 2.5-inch version. I think we are going to see a migration towards these PCI Express drives. You've also got sort of platform level support with Intel bringing M.2 slots or explicit support for these drives into its 9 series chipsets. And there are rumors that Skylake is going to take that a little bit further. That's Intel's next generation CPU, and actually have provisions for storage connected directly to the CPU, which you can do now with X99 and the Haswell E platform, but it's not really built specifically for that. But some of the rumors that we've seen have Skylake desktop chips having a dedicated storage link in the processor. So I think that, you know, we're sort of moving in that direction. But we might not get there terribly quickly, and we might get there just because that's the direction the industry is moving, not because there's a really definitive need for it. And I say that based on a bunch of testing that we did with a stack of sort of contemporary SATA drives, and then sort of 3 different classes of PCI Express SSDs. You know, PCIe SSDs come in a lot of different configurations, even though there are only a few on the market. So the sort of the lowest end drive that we tested is the Plextor M6E, which is based on a Marvell controller with a 2-lane PCI Express Gen 2 interface. So it's a good match for the 2 lanes that you've got in the 9 series chipsets that are dedicated for PCI Express storage. The thing is that it's not really that much faster than serial ATA. So serial ATA tops out at about 600 megabytes per second, and 2 lanes of Gen 2 PCI Express is going to give you about a gigabyte per second. So it's not a big step up. The controller technology is not something wildly new, but it's sort of the first commercially available SSD or PCI Express SSD that was out there for consumers. And it's a very easy drive to use. You can plug it into pretty much any PC. It comes with an M.2 adapter card, so you can just plug it right into a standard full-size PCI Express slot. There are no really issues with booting the thing. It's got, you know, drivers built in. It's a standard AHCI device, but it's not particularly fast. So the next one up from that we have is the Samsung XP941. And this is really an OEM-only product. It was meant for system builders and notebook makers. Samsung doesn't really sell this directly to consumers, although you can now buy it at Newegg. This one has a 4-lane Gen 2 PCI Express interface. It has double the bandwidth of the Plextor drive. And there's actually a Gen 3 version that we just got in our labs today. Actually, it arrives, the SM951. Which is a 4-lane Gen 3 interface, which has quite a bit more bandwidth. So that's kind of a drive that's accessible, a drive that's in some of the Mac systems that are out there now, but not something you can easily buy, and something that, you know, is not really going to do as well in, you know, let's say an off-the-shelf 9 series motherboard whose M.2 slot has only half the number of PCI lanes running to it that this drive can take advantage of. So this is kind of something that's really meant for OEMs, or if you've got something like an X99 system where you've got more bandwidth to an M.2 slot, or if you're going to be using one of these adapter cards, this is kind of more appropriate for that. And then the last drive, we kind of shot for the moon and went with a super high-end $2,400 Intel server-grade PCI Express SSD, which, these other drives are on these little M.2 gum sticks, which, they call them gum sticks because it's kind of like the size of a stick
Stick
of
of
gum.
gum.
And this Intel drive is, on a half height, half length PCI full size expansion card. It's got a big single slot heatsink on it, a 25-watt power envelope. So it's a entirely different class of drive.
Yeah.
And this one's got a 4-lane Gen 3 interface. It's built for servers. It's an 800 gig drive. It's got a lot of spare area set aside, as most server class drives do. We just kind of wanted to see what would happen with the fastest possible SSD we could get our hands on.
Yeah, Jeff, tell me. Let's talk a little bit about this too, because there's SATA as a connection, and there's PCI Express as a connection, and then there's this protocol difference too, right? You said the first two drives use AHCI, which I associate with SATA, right? What?
Yeah.
But that's not really the future, is it?
Not for PCI Express storage, no. They came up with, a few years ago, a new protocol called NVM Express. And it's designed specifically for SSDs. AHCI has been around since sort of the mechanical hard drive era. It was never really conceived for solid state storage, which is very different than a mechanical hard drive. There's a lot less latency, and you can get away with a lot of things in AHCI that you can't with a mechanical drive that you can't with a solid state drive that will sort of expose the greater overhead of the old protocol. So NVMe is super streamlined, and it's designed to be really scalable. The example I use in the article is that AHCI is limited to a single command queue that's 32 entries deep, which is fine if you're using a hard drive, and honestly most desktop tasks only have a queue depth of about 4 or less. So you don't actually need to scale up to these crazy queue depths unless you're in something like a server environment where you have a much more demanding workload. And NVM Express supports 64 individual queues, and each queue can be 64K entries deep. The 64K for both. So 64,000 queues and 64,000 entries per queue. So it's designed to scale up with these solid state drives, which are basically just massively parallel arrays of memory chips. So they do scale well with additional capacity and additional chips, and now they have a protocol that's a very low latency design and built to scale in the same way.
Yeah, so Jeff, this reminds me of the difference between DirectX and OpenGL versus like Mantle, Vulkan, and DirectX 12, where you have like these old APIs built to program things in a certain way, and it's kind of a serial bottleneck, and then you build something that's like lower level, more parallel capable, and it scales up much nicer. So it is actually lower overhead too, isn't it, in NVMe?
Yeah, they basically stripped out everything that was related to hard drives. I mean, AHCI has a whole bunch of baggage that is in the standard because it's the same standard that's been around, for more than a decade. Whereas this is specifically architected for SSDs, so it only includes stuff that you need for a solid state drive.
Yeah, and I kind of expect that over the long run, that literally the way that software is written, the way the operating systems handle storage, and maybe even the way that systems are architected will have to change to take full advantage of what you can do now with storage with flash arrays like this. But this is a huge step toward that.
Mm-hmm. Yeah, I mean, it's the kind of thing that will start in servers and workstations, or has already started. And the sort of the challenge that we face when testing these drives is trying to find cases where someone with a desktop system might benefit from a scenario like that, which is, it's hard to come up with scenarios to stress a $2,400 server grade drive. But we tried.
Well, and this is the product of a lot of work, right, Jeff? I mean, how long you've been working on this? Is the beginning of a new benchmark suite for storage, right? You've been working on this how long?
Oh, on and off for months since last year. It's, the kind of thing you chip away at and hit a roadblock and have to go figure some stuff out or wait for emails. You put it down, go review something else. So yeah, it's been a long process. The old suite was really, really old, and Duke Nukem Forever and Portal 2 were the games we used to test load time. So that'll sort of put the time frame. up there for you.
Right.
So this is long overdue for a replacement. We basically threw out everything in the old suite and came up with a whole new range of tests, a whole new range of games and load time tests, and tested these 3 PCI Express drives and then this stack of SATA drives. And just for kicks, I dug up an old Intel X25M G2 drive, which is actually a SATA 3 gigabit per second drive. I think it's about from 2009, so about 6 years old, just to kind of see, what the difference between that drive was and the SATA SSDs, and how the PCI Express drives compared as well.
Yeah.
And the results were interesting.
Yeah, and Jordan, we have been trying for a while with the old suite and things in between to find places where, like, buying a faster SSD, one that we could benchmark as faster, translates into a performance difference on the desktop that matters to you, right? Because otherwise it's just buy the cheapest thing per gigabyte. And
Exactly.
Jeff has worked really hard to attempt to come up with some tests that will demonstrate that, or not, as it may be, by duplicating what you really would want to do with your PC, and then, having some potential for goodness. So
Is that the TR RoboBench?
well, we got several things.
That's part of it, yeah.
So
Yeah, I mean, that's the thing, is it's easy to come up with tests where you can see where a PCI Express SSD is faster than a SATA one. We sequential tests, random tests. We've got a bunch in the article where it's very clear that not only are there big differences between the PCI Express drives and the SATA drives, but between the different PCI Express drives, there are huge differences. Part of that is just the bandwidth that they have access to. We've got one drive that has double the bandwidth of the other, and then the Intel drive has, again, double the bandwidth again. One of the interesting things we ran into is that, you need to use multiple threads to get the most performance out of these drives, and in some cases you need to use a lot of threads. So for this Intel server grade drive, you don't hit their peak advertised performance numbers until you've got 128 simultaneous requests hitting the drive, which is a lot more than kind of the 4 that would be typical in a desktop system. And that 4 is kind of like at the high end of what would be typical. So you can measure differences, and we've got, in some cases, I'm looking at the sequential write speeds where this Intel server grade drive has triple the write performance of the Samsung 4-lane drive, which is in turn, 200 megabytes per second faster than the Plextor drive, which is only a little bit faster than the SATA drive. So there is a big range of performance in some of these tests. But then if you go and look at things like access times, the gaps are really small. You're still looking at fractions of a millisecond difference between access times. And that's because, PCI Express might give you a much wider pipe to pass data through, but even with a lower overhead NVMe protocol, if you have a lighter random load, you're not going to see substantially lower latency. So it's an improvement, and the kind of improvement that if you're in a server environment and serving lots and lots of requests is really important. But on the desktop, it's certainly nothing like the jump from mechanical drives to solid-state drives.
So should we talk about I guess the thing to be said about the synthetic tests is, you kind of said it, which is the Intel drive in particular and some of the other PCI Express drives were measurably faster in sometimes dramatic fashion when you're using a synthetic test, right? But let's talk about is that enough then? We can move on to the real world tests and talk about what that means for you?
Yeah, well, I guess the other real world, it's RoboBench is kind of a weird in-between test between a real-world test and the synthetic benchmark. And what it is relies on the Windows robocopy command, which is basically a multi-threaded file copy command. We set this up with a bunch of different test configurations with an accompanying RAM drive, so we can use this command to measure read performance, write performance, and copy performance with actual real-world files. Movies, MP3s, raw images. We had all of those collected in a media set, and then I had a whole bunch of TR work files, some programming files, stuff like documents and spreadsheets, a lot of much smaller files. and those are in our work set. So we were able to test read speeds, write speeds, copy speeds with these different sets and at different queue depths. So with only one thread and with 8 threads running in parallel. So it's a real world scenario, but it's a straight up sequential transfer or of files. So it's a little bit in between the two. So there we definitely saw differences, but only with the bigger files. When you're moving a lot around a lot of small files, you don't get the same benefits that you do if you're moving, let's say, around a bunch of sort of multi-100 gigabyte movies. The PCI Express drives are still generally faster, or in particular the Intel one was at least faster, but its margin of victory was, a couple of megabytes per second, and the total speed, you're looking at, 130 to 150 megabytes per second in some of these tests, instead of, I'm looking at some as pushing over 1400 megabytes per second in others. So that's a situation where, it's pseudo real world. But the real world stuff we looked at were boot times, load times, and sort of how long it took to open large data files in the kind of desktop applications that you might want to use. So the boot times are kind of interesting because we measured these with a stopwatch this time instead of the old method we used, which tracked how long Windows took to actually load the operating system. So it factors in the initialization time for the drive in addition to how long it takes to load the OS. We found here is the Plextor and Samsung PCIe drives are actually really fast. The Plextor was faster than everybody else by about 3 seconds. And the Samsung drive was, about a second faster than the fastest SATA SSDs, which were separated, they're sort of clumped together in a group about 3 to 4 seconds. So the SATA drives are reasonably fast, but the Intel drive actually took longer to boot than most of the SATA drives. And I think that's part of that is just the initialization required for it. A server SSD is not something that requires really fast boot times. And also there's some additional firmware work that's required to get an NVMe drive like this Intel server SSD to actually boot. So I think some of the hooks required in the firmware may actually slow down the boot process a little bit. But I mean, you're only looking at a difference of 5 to 10 seconds, which for booting a system, I don't know how often people do that on a daily basis on a desktop, but it's not a huge detriment certainly. But I don't know if they call these interesting or boring results. So we have a whole bunch of load times for a 4K video file, a really large high megapixel image, a giant spreadsheet, a Visual Studio project, and then a whole bunch of save games in Batman Arkham City, Tomb Raider, and the new Lord of the Rings Shadow of Mordor game. And the performance is basically a wash across the board. The drives are all, PCI Express drives, SATA drives, even the really old Intel SATA drive are all within about a second of each other in terms of load times, which is not something I was expecting. I was a little disappointed by the results, although at the same time a little bit vindicated that all the old results that we have showing that there's no difference between SSDs and load times is sort of still legitimate with all of this completely new slate of apps and games. But it is kind of underscores the point that, if we were testing a mechanical hard drive, these were the areas where you would get big gains. You would get, load times being cut in half or being cut by 50%, going from a mechanical drive to an SSD. And going from a PCI Express or a SATA SSD to a PCI Express one really doesn't give you anything, just as, the last, I don't know how many generations of SSDs haven't really performed or improve performance in these types of tasks.
Yeah, it is a little depressing to see these games take, on the fastest hardware you can get, take a minute to load a level or more, right, in some cases. Or just that you can't, the faster hardware doesn't make it faster, right?
Yeah.
And I think some of that comes down to the way that they're built. There are a couple things that people are talking about. One of them is in things like Vulkan and maybe DirectX 12, I think you can maybe save pre-compiled shaders from the GPU, so you don't have to do the shader compilation when you're loading, which is part of the load time delays right now in some cases. And then the other one is games could be built to stream textures from storage instead of preloading things, if you can assume fast storage with NVMe and PCI Express as the norm. And in those cases, then you could actually get way faster performance, way faster loading, way more instant response, but you kind of have to build your software predicated on the presence of better hardware that will allow that, or better APIs, or both. So that kind of...
That's going to be tough.
Yeah, I mean, it kind of stinks.
Because you got to make two assumptions there. First, you have to assume that someone has an SSD.
Yeah.
And then you have to assume that it's an SSD with substantially more bandwidth than SATA can provide. So to take advantage of a PCI Express SSD is, yeah, it's sort of like the problem with games and graphics hardware. Developers have to assume a certain baseline, and the baseline for storage is probably going to be, fairly sad for a while if a developer wants to target a wide swath of the market.
Yeah, well, it's gonna take time, but
Intel's working on it.
Right.
I've talked to them on a couple of occasions. They're actually demoing stuff for game developers and showing them that, hey, look, this is all that you can stream off of a drive in real time using the technology that we have right now. So it's, a few years from now, I think we'll probably have maybe not games that require an SSD, but certainly games that, you can do more if you have an SSD installed in your system, and maybe use higher resolution textures or enable certain effects that you can't without.
Yeah, so I think Jeff, that the next thing that we should probably do is talk about the first consumer PCI Express SSD that you also reviewed shortly after this, which is a nice sort of follow-up, because the fastest drive by far in this test was that Intel data center drive, right?
Yeah.
And then we're busting it open with the 750 series SSD. So what did Intel do here?
They basically repackaged that data center drive. It's based on the same form factors. It's got the same 4-lane Gen 3 interface. It's got the same proprietary controller chip. They switched the memory. So the Intel server drive that we reviewed is the DCP 3700, which is their high-end server drive that has, incredibly high endurance and all that sort of good stuff. This, they use sort of more conventional NAND that wouldn't make the grade for a high-end device like that, but it's still plenty for a standard desktop. You still get a 5-year warranty and a 70 gigabytes of writes per day for the length of that period endurance rating, which for a desktop system and probably even a lot of workstations is plenty. But otherwise, it's basically this server grade drive. They did a lot of work on the motherboard ecosystem to support it. So they've been working with motherboard makers to support booting from NVMe devices, which was really that part of the the thing that delayed that initial article on performance, was the fact that this Intel data center drive wouldn't boot in a lot of the motherboards that we have. But Intel worked with firmware providers and the motherboard makers, and now most, if not all, 9 series boards can boot off the 750 series SSD in addition to other NVMe drives, as long as they're running the latest firmware. They also worked with motherboard makers, which we don't have any boards yet that actually include these ports, but this drive does come in 2 form factors. You've got this add-in card, and you've got a 2.5-inch form factor that's actually 15 millimeters thick, so it's about double the thickness of most SSDs. But that uses a special SFF, the name escapes, or the specific number designation escapes me now, but it's basically a cabled PCI Express solution with a special port on the end, and it's the same kind of thing that they use in with SAS devices and in servers. They actually think that this is going to be more popular than the add-in card version, because this is targeting high-end systems, and the idea is that if someone is using a rig with multiple graphics cards, you're not going to have those PCI Express slots available for an SSD, and even if you do, they might not be PCI Express slots that are connected to the CPU, which is what you want, because you want to be able to take advantage of those Gen 3 lanes and having 4 of them, which no core logic chipsets have enough bandwidth for right now. I mean, even in the chipset, there's not enough bandwidth, and then the link between the chipset and the CPU doesn't have enough bandwidth either. So there's really no way to run this properly without connecting it directly to the CPU.
So this drive, I assume, performs like really nicely. Um, the let's talk real quick before we get into that about the costs, right? Because uh, this can't be. I mean, if they were taking their data center drive, even with lower shelf NAND, like this can't be cheap, right?
No, but it's not as expensive as I figured it would be. It's the 1.2 terabyte model is $1,029, which works out to about 84 cents a gig. And there's also a 400 gig version that's going to be 389 or about 97 cents a gig, which is a lot in the context of these really cheap SATA SSDs that you see out there. But it's actually fairly comparable to the pricing for that Samsung drive we just discussed, and for the Plextor M6E, and for a lot of if you look at sort of the high-end SATA SSDs like the Samsung 850 Pro, they're all kind of in the same ballpark on a price per gig basis. So it's a high-end desktop drive for sure, but it's not as expensive as you would expect from basically a repurposed data center drive. And that's just the list price, and no SSDs stay at the list price for very long.
Right.
Even Intel's last sort of data center trickle down drive, the 730 series, is regularly on sale at Newegg right now for much less than its manufacturer's sort of suggested retail price. So I would expect even these prices to fall a little bit.
It looks like
So yeah, I mean, for the performance, especially since it basically costs about as much per gig as other SATA SSDs, offers much higher capacities, and then also much higher performance.
it looks like they're really conscious of this the dollar per gigabyte mark and tried to stay under that. But how cheap are like sort of mainline SATA SSDs now though on a cost per gigabyte basis?
They're about the Plextor M6E was just under $1 per gig, and the Samsung XP941 was again, we tested the 256 gig version of each, and the prices for those were in sort of the $215 to $230 range.
But if I go buy like a cheap 2.5-inch SATA plug drive now, it's like half that or less, isn't it?
Yeah, it's sort of 30 to 50 cents per gig for sort of the mid-range to low-end stuff.
So
It
there's
sort
just,
of depends on what you find on sale. So it's a different, you're paying twice the price, which actually is not that much if you consider that in some of these cases you're getting a lot more than twice the performance.
right.
The issue is just in some cases you're not getting any more performance at all.
Right. So let's talk a little bit about that performance. So you've got I guess we've got a full set of data here. What is there anything we want to highlight? I mean, I kind of can predict what the real world results are going to look like.
Yeah,
but
exactly the same. This is kind of an in-between drive in terms of performance. It's not quite as fast as the data center drive. There are certain things the data center drive does really well just because a lot of the flash it has set aside is over-provisioned area, which means that it can, deliver a lot more random writes at really high speeds before it slows down, for example. So in a lot of cases, the 750 series is not as fast as its $2,400 counterpart. But in a lot of cases, it's almost. The peak random write speed is just a smidgen slower. Some of the sequential speeds are only a little bit slower. And this drive is consistently faster than the Samsung that we tested, and quite a bit faster than the Plextor. So as a sort of consumer grade drive, it's absolutely the fastest one we've tested. We'll be testing Samsung's newer Gen 3 version. But I don't expect, given the margin that we're seeing, especially with random I/O, the Samsung drive is reasonably quick with sequential transfers. But random I/O, if you look at the iometer database results that we have, the Intel drive is just in a completely different class. And even a lot of the PCI or SATA SSDs have much better random read and write performance than the Plextor or Samsung PCI Express drives, which is kind of interesting. I mean, just because you get this faster PCI Express interface doesn't mean that your controller architecture or your NAND array is necessarily up to the task of delivering substantially better random performance, even though it can push much higher sequential speeds.
Yeah, and you look at these numbers and you feel like this is the future again, right? Like it's kind of like back in the days when Intel first shipped out some of the first SSDs with their own controller. They were kind of showing the way for the industry and pretty open about that, right? This kind of feels like the same thing.
Yep. Yeah, no, I mean it's absolutely the future of storage, but it's kind of a chicken and egg scenario for kind of standard desktop use, in that it's just challenging to find workloads that need this in a workstation context, or if you know that you're very specifically storage bound, this is probably a dream come true for a lot of people, because it's, you can basically get the performance of a multi-drive RAID array out of a single drive that you can plug into a system. Apparently you can run multiple 750 series drives in a RAID array as well. You lose the ability to boot off them. But if you want like a really insane storage configuration, you can apparently pair up multiple drives.
Be right back.
Yeah, I mean it's sort of a an academic thing at that point to just let's see how fast we can get files to transfer. But it's for a workstation user, when we were talking to Intel, they were talking about car designers who are working with really large data sets, or when doing fluid dynamics, there are large data sets that require fast access. It's just a question of how long those things will trickle down to desktops, and whether or not there's reasonable consumer 4K editing workloads that it can even use this kind of horsepower is debatable at this point.
Yeah, well, I capture video straight from video cards in basically uncompressed format and save it to a RAID array, and I hope to do that at some point 4K 60 hertz or better. And so
that'll do it.
I've got one of those DC3700s sitting in a box over there, and it's like, the problem is you need like terabytes, just because otherwise you're not going to have very much video if you're capturing it like that,
Well, that's a good thing, NAND is getting cheaper, and you can make SSDs faster by just putting more of it in parallel on a drive. So the fact that the NVMe Express protocol is sort of, the foundation is laid there for scaling up performance. You've got PCI Express, which is a multi-lane interface that you can just add more lanes to get more performance. The potential to scale up from here is all there.
Yeah. Yep. No, it sounds good. And so this is kind of the first. When are we gonna see more really good, hopefully really good PCI Express NVMe drives later this year?
Hopefully. We haven't heard a lot about drive makers actually releasing NVMe Express drives. We've heard a lot about controllers that are AHCI and some controllers that are NVMe Express, but like with the Samsung SM951, which is their Gen 3 drive, they originally, when they were talking about it this last summer, were talking about it in an NVMe Express context. I think some OEMs may be using it in that configuration, but the version that we have and the version that seems to be available through sort of gray market channels is an AHCI implementation. So I think that, now that Intel has done the work to get motherboard firmware up to speed, we might see more NVMe drives, but right now 9 series platforms are the only ones sort of guaranteed to work with it, so that might put a bit of a damper on it, especially since we haven't seen a lot of PCI Express drives. But I would expect by later in the year, hopefully we will see at least a couple more, and we will probably have a lot more AHCI based PCI Express SSDs before then.
Cool.